It's actually appropriate. So my heat came on. It gets really warm in here. I have a little note to myself. There's a number of you who have not turned in 1 or 2 or 3 labs, so please make sure you get the labs in. Yeah. So we got a week. We're done Monday. So get it in before that, so I don't have zillions of stuff, but most of you have been getting it in, and you're in great shape. So use this week. Let's end all really strong. So therm means heat. So we're really going through a couple topics here tonight, but they all come together or all go together. So enthalpy, we actually saw this word when we did liquids. Enthalpy is symbolized with a delta H, and I mentioned it then. Enthalpy is a measurement of heat. So thermodynamics is the study of heat relationship. Chemical reactions always involve a change in heat. And so that's what enthalpy is. It's always a heat change. You can never actually know how hot it is. You can only know the change in heat. So it's colder outside. The east wind's going to start up. It's going to get colder. We can measure temperature, but heat is more the difference between this and that. So this triangle means change. It's a delta sign. And so we never actually say heat. We always say delta H, which means heat change. The first law of thermodynamics is conservation of energy. And since we are actually a form of energy, right? E equals mc squared, Albert Einstein proved that matter is just a form of energy. Conservation of energy is the idea that you can change one form of energy into another. And so our hydroelectric dam uses the movement of the water, so kinetic energy. So energy or movement gets the turbines moving and creates electrical energy, which we use to light up our life and turn on all our devices. A lot of us are using batteries, so on our phone or our laptops and stuff. And so that's using a chemical and oxidation reduction reaction, actually, so chemical energy. The key to this is 2 things. One, the word enthalpy, and then these terms, exothermic and endothermic. And I'm pretty sure I mentioned this when we did liquids, but it's actually the centerpiece of today's lecture. So exo means exiting, or heat is exiting. So in terms of chemistry, that would mean it's a product. You're losing heat, so heat is exiting. Endo means heat is, heat is into the reaction. So it's absorbed is the word they almost always use, or it's a reactant. And for exothermic, the word that you'll probably hear me use just automatically is releasing. So heat is released, or it's exiting. So that's where the term exothermic, and endotherm again means heat. All right, the other thing with that, before we talk about entropy, is there is also, besides numbers and units, which is what we've been doing all term, so these will have units, there's also a sign. This is like your bank account. When money exits your bank account, it's considered negative. So when heat leaves a reaction, it's negative. So we say it's a negative delta H. When something enters into it, the heat goes into it, we call it a positive delta H. So when we get to examples, which we do a lot of over these 4 pages, and your study set and stuff, I think your study set might actually be 3 pages. Might be our only 3-page study set, but. All right, there's a second term. which is entropy. And entropy is symbolized by S. You can actually know just S, the entropy of something, in one word. Does anybody know in one word what entropy is? It is disorder. Yeah, I guess some people, it's usually said as disorder, but chaos is the idea of it. Yes. So entropy is a measurement of disorder. There is only one law in the universe. All the other laws come from it. And there's only one true law, and it is this one. And that is that the disorder is always increasing in the universe. Increases. And so our universe is always expanding. Our life is always expanding. And there's so many jokes, so many cartoons. So those of you who've been enjoying the cartoons or understanding the cartoons, tonight's lecture just opens a whole new realm of them to you because of enthalpy and entropy and equilibrium and kinetics. So there's a positive and negative. Disorder is a positive thing. So you can measure the entropy. We're going to be doing it with chemical reactions because it's chemistry. And so we're going to be looking at the change in entropy. So that's why the triangle is there. So again, the triangle is delta, and it means change. Positive is an increase in disorder. Disorder is a good thing. Negative is a decrease in disorder. So I joke. If you read any of my stories, the aspirin story is based on what really happened to me when I was in Nepal. But in Nepal, there is no word actually for down. There might be now that somebody made up, but historically, there was no word for down. And if you ever go to the Himalayas, you will finally understand. Joey and I were like, so there's mati and na-mati, meaning up and not up. And every time you've gone up, you've gone over the highest point on the path, and you should be going down. And you do go down, but then you keep going up. It doesn't make sense, but it does make sense. Once you're there, you just get used to it. So there is actually only disorder. So you either have more disorder or less disorder. And that pretty much kind of feels like our life in 2020. This is perfect. Sometimes you will hear me say this as order. So less disorder is order, but truly there is no such thing as order. Everything's always got some kind of chaos and stuff. So for chemistry, again, we're looking at this in terms of chemistry. You're going to look at the state of matter. This is which state of matter is going to have the most entropy. Which state is all about entropy and chaos. And disorder is gases, right? So from solid to liquid to gas, gas has the highest entropy. Enthalpy is different. Enthalpy you actually have to measure from the temperature change. These are two separate terms, and we'll see how they play out when we get to our examples here. So solid is pretty much you're just sitting there. It's kind of how a lot of people are in existence. There's no entropy and stuff. And then liquids are flowing. Gases, though, they definitely have a huge change in entropy. So we're going to walk through these examples and look at them. There is actually a third term, and we're not going to go through it, but it is actually might be the first American who won the Nobel Prize in chemistry. In fact, when they do stamps of famous Americans, he always, scientists, he's always one of the stamps, and it's Gibbs free energy, and it's a term that combines enthalpy and entropy changes in a study in chemical reactions. But we're just going to look at each one of these. So for the delta H, the enthalpy, that's going to always be given to you. And these equations show you a couple different ways. So let's just look at the first question for each of these. If it is just shown within the equation, This means that that's the heat. So the units for heat are either going to be kilocalories or kilojoules. So joules is actually the true unit. The metric system uses calories, and so these are like calories of food, nutritional calories. So the whole myth of calories in food that we've gone way off on for the past 100 years, it comes from people wanting to sound intelligent, and they took the term from physics and chemistry as a measurement of heat, and they applied it to food, and now people became obsessed with it. It's not the calories in your food that matter. It is actually the quality of your food and where it comes from. So having a 100-calorie, highly processed bar that has everything added to it and having a 100-calorie apple that's a real whole food, they're not the same thing. Your body's going to process them totally different. All right. Anyway, so if it's given within the equation, heat here is a product. So from what we just said, the sign would be negative. So heat is a product. This is exothermic. So it's shown, right? Here's our arrow. So before the arrow is reactants, after the arrow is products. All right, let's go through each of them with the exo-endo, and then we'll come back and do the entropy. So on the next one, I actually write the symbol delta H, and same on the next one. So if it actually shows you delta H is always written as an afterthought after the equation. In that case, you just look. So like on number 3, it doesn't give you a sign. That means it's a positive. If it was a negative, the negative would be there. So on number 3, that is endothermic. On number 2, that is saying it's less than 0. Delta H is less than 0, so it's telling you it's a negative. So it's exothermic. So exothermic means either that it's shown as a product or that the delta H is shown as a negative. Endo, it's a positive. We'll do number 4 together in a moment. So let's go through these equations that wrote out and look at the disorder. So disorder, we have to look at states of matter. Now, the first example I gave you, they're all gas. So if everything's in the gas state, there is always a change in entropy, always. If they're all gas, then you look at the moles. Only if they're all gas, we should say that, only. So again, we'll see examples. We go through this, and then your study set and your worksheet will give you examples. All right, so I have 1 plus 5. So on this side, I have 6 moles of gas. And on this side, I have 3 plus 4. So on this side, I have 7 moles of gas. Gas is like children, small children. It's chaos. You have a house with 6 children. Yes, it's chaotic. And then you have another baby. You have more chaos. The side has much more disorder. You don't care about the laundry being folded. So our disorder has increased. And the sign, disorder is actually what we're all moving towards. It's positive. Think of it this way also. Well, this is what I used to always say. You know, you come to school, we're in class, and then when you get home, what do? You just drop all your stuff, and you just want to slump down. You just want disorder. You don't want to put everything away nice, neatly. Of course, now we're all in our houses, so we don't have to go home to be like that. But we do. You want to be slumping there, right? All right, on number 2, same idea. So again, here's our arrow. So on this side, we have 4 moles. And on this side, I have 2 moles. So in this case, we kicked some of them out. We organized it. We compacted it into just 2 moles. So this would be, it's moving towards order. So again, how I asked it in example 1 is the correct way. But sometimes I am incorrect and I don't even realize I do that. So if I ask if it's increasing or decreasing, this would be a decrease in disorder. So, or it's moving towards order. And the sign would be negative. These signs are independent of each other. You can get a negative positive, a positive negative, a positive positive, a negative negative. So we figure out exo endo, that's going to be given to you with the delta H, or the calories or joules. And the order disorder, we look at states. Now on example 3, we don't count because we have a liquid changing into a gas. So that all means liquid. So we are moving towards disorder. And so this would be positive. All right. It's just, you'll have a couple of these on your study set, and that's the idea. I think we'll run into a few of these. So deposition, perfect time for this. So usually we have snow, and then we have a snow day that I'm worrying about, and I have to figure out how to reschedule everything for finals. But we don't have to deal with that this year. So we don't have snow. So up on Mount Hood is gorgeous right now because of all the snow. Deposition, anybody remember what deposition means? It's a change in state. It's water changing states. So deposition is snow. We're suddenly forming H2O as a solid, and it came from water vapor. So it's very rare for it to happen here in Gresham because we're really close to sea level, and so the pressure is not right, but you need the perfect temperature and pressure to skip the liquid state. Here in Gresham, we usually get freezing rain, so the gas condenses to the liquid and the liquid freezes. Mount Hood, because of the elevation, right? That's why the mountains get snow. The elevation means the pressure. Remember all that stuff we talked about, atmospheric pressure and stuff. So this would be our equation, would be the H2O gas going to a solid. This is exothermic. And the way I know that, here's your definition for entropy, by the way, if you want the fancy, a thermodynamic quantity representing the unavailability of a system's thermal energy. That's like a crazy definition, or it's the lack of order, which is interesting definition since there is no such thing as order. So why don't they just say, all right, a gradual decline into disorder. Why don't they just say point blank it's disorder? I don't know. If we go from a solid to a liquid to a gas, we're going to add heat, right? So if you have a snowball and you're going to add heat, you would melt it. We're going the other way. We're going from a gas back to a solid. So this is going to be losing heat. So it's going to have a negative delta H. So the gas had the heat, and we're definitely moving towards order because we're moving towards the solid, which is negative delta S. Questions? It's just the idea of entropy and enthalpy. And introduced it with that because to be able to fully appreciate equilibrium, we have to understand enthalpy because it has an impact on it. So let's go on to equilibrium. So we actually talked about equilibrium a little bit with, does anybody remember? Chemical equilibrium is this. In a moment, it's this. It's arrows that go both directions. So it's the myth that I already commented on when we did acids and bases. So when we learned chemical reactions about a month ago, all of our reactions went one direction. Most reactions actually go two ways. So chemical equilibrium is two-way reaction. Most reactions are reversible. So terminology. When you go this way, the way we've always been going with our chemical reactions, this is called forward. In fact, there was during an office hour, I kept saying that, and it confused a couple people because they were like, what are these words? But that is the forward direction. You're not going to hear me do left and right because of how the screen is. I am actually flipped on your screens as I would be in class. So your lefts and rights will look funny up here. But when we're moving from, this is the reactants to the products, that is called the forward direction. So in this equation here, hydrogen and iodine are the reactants, and 2HI are the products. Another comment, well, we'll get to that. So this is the forward reaction. That is called the reverse reaction. Let's write it below it. Or backwards. You guys like the term backwards, but it is called the reverse reactant. So moving towards the reactants is reverse. So chemical equilibrium is this idea that we mix the hydrogen and iodine. And this happens in a femtosecond, which is a million billion, so 10 to the negative 15th of a second. So a snap of a finger actually takes like a millisecond, a thousandth of a second. This is 10 to the negative 15th of a second. Those two are colliding and reacting and making the HI. But the HI keeps breaking down into hydrogen and iodine. So the reaction's going both directions at the same time. It's not that it goes forward and then it goes backwards and then it goes forward and then it goes backwards. It's going forward and backward at the same time. Why it's called equilibrium is it hits a point. It's not that the reactants and the products are equal. It's just it hits a balance point. So it's like these rocks. Like here, you actually have more here because our balance point, our fulcrum, is at a different place. I've never been able to do this balance thing. I'm amazed at people who can figure it out. But and how equilibrium is expressed is by the equilibrium constant. The correct term is equilibrium constant expression, which is a K, capital K for constant. It is a ratio. That is the key. It is a ratio of how many products to reactants you have. It is molarity over molarity. And again, it is the products are always in the numerator. And we're going to do a couple of these so you see the idea, but that's all it means. It's a ratio that tells you a comparison of your products to your reactants. And it's molarity. So that's what those brackets mean. You only include gas and aqueous. Because what happens in equilibrium is the molarities are going to change. So I guess today's theme is kind of this idea of change. And gases can definitely change. You can have expand them and contract them, right? They compress. Aqueous, we can add more or less of. Liquids and solids, they're either there or they're not. It doesn't really matter. So for equilibrium to be established, all components must be present, meaning reactants and products. So all components must be present. So if you're missing any part of it, it's not at equilibrium. So like down here on this one, when we write our equilibrium constant, let's actually just do it. Whenever we see, this was something a student actually showed me, and whenever you see a solid or liquid, you're going to lightly cross it out because it doesn't impact the equilibrium. So the assumption is if we're talking about equilibrium, the system acquires equilibrium in that femtosecond in 10 to negative 15. So as soon as you mix the things, the equilibrium is established. When we did the lab, that would always confuse students because they're like, how long do I have to wait? How long do I have to wait until I can write down my observations? And I'm like, it already happened. And so, yeah, we will write K equals, and we write our reactants. We cross out, we write our products, magnesium. You do show it as an ion in the bracket. And then you show the hydroxide. And what happens with the koi fish is they become an exponent. So the coefficient is no longer inside the bracket. The coefficient is the exponent. So this 2 is up here. It's just how it's done for the K expression. Now I said it's a ratio. We have no reactant. So you can leave it how it is like this, or you can say over 1. You can't have over 0, that's impossible. So half of you will just leave it blank on the bottom, and half of you will need to say over 1. For equilibrium, what I mean by this statement up here, the equilibrium, the solid is present, as are the ions. If the solid all dissolved, you don't have an equilibrium. So there is some solid there. It doesn't matter how much solid. So that's why I say you don't include the solid. What matters is the concentration of the aqueous ions or of the gas. It's a very odd concept, and it doesn't really matter that much for what we do. What you really just need to know is you cross out the solids and liquids so that you don't try to do anything with them. For equilibrium to be there, the solid is there. It just doesn't matter how much. All right, for B, let's write our K expression. So K equals, so again, these are my products, and the products are always in the numerator. The state of matter, we just need so we know it's there. So CH4. There's no coefficients, we just write CH4, and then you're multiplying it times the H2O. So it's, sorry, I'm trying to find the word. It's, I guess that's another one of the mistakes students will often make, because in the equation we say this plus this, but in the equilibrium we're suddenly multiplying the two products. And then we say over, and we put our reactants. So it's the CO, and then the hydrogen. And the hydrogen will be taken to the third power. And that third power is because of the coefficient 3 there. All right, we're going to do one more. We're going to do it for our original equation up at the top of the page, so you kind of see the idea of it. We'll do another one down here. So K equals, and again, it's a ratio. It's always the products over the reactants. So my product is the HI. And we're going to raise it to the second power because there's 2 of them. So it's HI squared. This would be important when we do math. I think there's one math problem on your study set. There's one here we're going to do. And the hydrogen and the iodine are in the denominator. In my 223 class, this is the very first lesson I do. And then we do math for the whole rest of the term based on this ratio. So in a biochem class, that would be like a 500 level class at a university. You do a lot of math with this ratio. For us, it's just that we write the ratio. It's always the products over the reactants. All right, what this means, it's a ratio, and it's more this number. It's a ratio, and ratios mean, because they're concentrations, it's always a number that's going to be positive. It's either the ratio is greater than 1 or the ratio is less than 1. Since it's always products over reactants, and really if that's, well, it's going to take this lecture, because it doesn't have the math. When we do the math, like the last one, the stoichiometry, you just kind of keep doing the math. This one's going to require you to do the homework and to try the best you can, and then just trust as we go through the homework. It's not going to be something where you can say, hey, can you look over my whole homework set? You're going to have to be here on Wednesday as we go through it and get the pieces and go back and redo it then. If K is greater than 1, it means you have more products. It means your numerator is larger than your denominator. If K is less than 1, what would that mean? It must mean, yeah, that the denominator is larger. So you have, like, instead of, you have a 4-to-1 ratio, or you have a 1-to-4 ratio. So you have more reactants. So that's all that's telling us. So we saw K's before. You go back and look at our acids. When we talked about weak acids and had a list of Ka values, and all the numbers were less than 1. And that is because weak acids do not ionize, don't dissociate very much. They do produce some product, but they're like 95, 98, 99% reactant. They only donated a little bit of their hydrogen. And actually, so when you go back and look at the acid stuff when you're studying, that might click a little bit for you. Yeah. I did the equilibrium at the end because most students actually pick it up. It might not feel like it between today and Wednesday, but by the time you leave Wednesday, you'll be fine. Whereas to end with pH, everybody starts feeling like, oh, I got all this stuff I have to do for all of your classes. All right, let's go ahead and do the math. And all right, so this is how much I have. I'm just going to write them underneath so I know this is my molarity. My PCl3 is 0.350, and this is what I don't know, and I gave you a value of K. So first thing you're going to do, if you're going to do math with this, and I would actually ask you, it would say state your K expression. What that means is we're going to write our K out. So on top are the products, so that's the PCl3. And again, these are brackets, but I'm okay with parentheses. This is like when we did, remember we wrote our Ka expression? We'd write hydronium conjugate base over the acid. It's kind of the same idea. We're writing PCl3 times the chlorine. It is the same idea. It's a K expression over the PCl5. So that is the K expression. It is unique for every problem. I didn't cross anything out because everything's gas. So you only cross out solids and liquids. All right, now you're going to plug in. So we know our K, 0.497 equals, we know the PCl3 is 0.35, 0. Chlorine's my unknown. I'm just going to call it X. And this is 0.860. So again, this is just like those Ka it is like the Ka problems because those were Ks. And actually, thankfully I have my calculator. So this is where you're going to cross multiply. So you're going to multiply by that, divide by that. We'll get a number. And we didn't have to square, do anything. All right, so 1.22. And the unit would be just capital M, molarity. So that's the idea of what equilibrium is it's a balance point. Every equation has its own unique balance point. So my question for you What does this K tell us about the balance point for this specific reaction? What does that value of K tell us? It's going back up to here. Well,
Less than 1.
the K is less than 1.
More
and
reactants.
So there are more reactants. So you can say more reactants, or the terminology you might see in some places is it's reactant favored. So a perfect balance, some students would say, is 1. 1 would be where the reactants and products are exactly the same. That's not actually a perfect balance. Every equation has its perfect balance point, like this up here. And what we're going to do now is we're going to see it has to shift. When change happens, you have to shift. And so this is a perfect topic for 2020 because we've all had to make a shift in our life. And we have all done it. And we found our new balance point. And we learned how to do it with a smile. Perhaps even smiling even more because we realized how important it is. So there was something else. Oh, there's one other thing that I do need to mention, and that will come up on the next page. This is temperature dependent. If you change the temperature, the value of K will change. And that goes back to the previous page on enthalpy, because every chemical reaction has a change in the amount of heat, either gained or lost. And so temperature will have an effect on where this balance point is. Delta H will not be affected, but the equilibrium will be affected. And so we're going to see that on the next page. Is there any questions? All right. Again, there is like my one class, the class teaches, the whole term is just on chemical equilibrium and doing the math. This is really all we'll see. You'll have a question, I think, in the study set that you'll do one math thing like that. So what this whole thing was building to is this page, which is Le Chatelier's principle, which is going to look really easy tonight because your teacher is going to do it with you. And then you're all going to go and do your study set, and you're all going to freak out because it happens every year. And so I'm laughing because I'm preparing myself for Wednesday when you're all going to be freaking out. Now, the good news is I have an office hour tomorrow evening, but really just do the best. It's our last one. And just know that as long as you try something, and a reminder, right? If you turn stuff in late, you lose 1 point, but yeah, no, do it. Let's get this one done and the worksheet, and you'll be fine. By the time you leave Wednesday, all of it will be fine. And in a week, Philip will probably be done because he always gets done with those things pretty fast. Philip, do you play tuba? Is that what instrument? I watched the video.
Yeah, I played tuba.
I only watched the band. So which guy were you?
I was sitting in the very front.
Okay. That's what I was wondering. I realized I'm like watching it and I'm like, I think that one's him. And I realized I don't really I feel like I know all of you. And then I'm like, I don't really know you. But that was fun. And the singing was beautiful.
Are you gonna watch to the end of it?
I have to, yeah, I'll go back. It became 5 o'clock and so I had to come here. I was scrolling because I couldn't understand.
Yeah.
Talking, obviously, because it's in Russian. Is that right?
Yeah. I'm glad you got a chance to see some of it.
Yeah. There were some of the songs I could recognize, even though the words were totally different because it was Christmas. Some of them were, universal carols of something. All right, so Le Chatelier's principle. This is the lab I videotaped. It is there on my YouTube channel. And so after tonight's lecture, we're going to get done early tonight, it looks like. You can go and do the lab. It's you just kind of follow along with me and then answer. And you're going to answer how we're answering these. And so there's color changes or things happen. And then there's some post-lab questions. So there's Dr. Le Chatelier, and he's wearing those glasses that have no things on them. The idea is if you stress or disturb a system, you and I are a system in equilibrium. We have a balance point, and if somehow it's disturbed, you must adjust. And so that's what we're going to look at to balance. Rather than saying to counteract, we should say to find that balance point again. So you and me always have a choice on how we react. Realize this is going to be in a test tube, and as soon as they're mixed, the equilibrium is established. So initially, let's say I just mixed the calcium and the bicarbonate. Well, they immediately react to form, and you would know because some white solid would suddenly appear. CO2 gas. Oh, this was the other thing we have to add on the other side on the previous page. And that is that it is a closed system. So there had to be a cork on it. My cat scratched me last night, which he hasn't done in 5 years. And last time he did it, 2 days later, I got really sick because half of the cats out there have a bacteria in their claws. So let's hope. And you want to know how I finally, after 2 days, I was able to Google it, and it was lavender oil. So it was like my hand got really swollen, but I put some lavender oil on it, and it was gone like in an hour. So hopefully I have lavender oil at home. All right. So we're in a test tube. The CO2 is formed. There is a cork on it, so the CO2 cannot leave the test tube, and some water. Now, the fact that this is aqueous means there was already a lot of water in there, and so you would not even perceive. Before we begin, what did I say we need to do?
Cross out anything that's not a gas or a liquid.
Yeah, so cross out our solid, just gently. You want to be able to see it, and our liquid. Another thing, these are some things students have shown me, is to put a bracket around your equation. This bracket represents your test tube. You cannot leave the test tube. So there's our equilibrium point. That's our balance point, and we're going to stress. So you're either going to add or take away. So we're going to add more calcium. So if we increase the calcium, there's more of it there to react. If you add something, it has to react. So it must react, which means it shifts forward. So the reaction goes in both directions, but we just shifted it and pushed it more forward. So that's it. We're shifting. This is not the same as on the previous page where we had a K value. Sorry. And we said, oh, this is reactant favored or product favored. This is, the equilibrium is there, and now we're shifting it. We're pushing it one way or the other. If you remove something, so the CO2 is over here, so if I take it away, if something's not there, you have to replace it. So if it's removed, you must replace it. So basically, you took the cork off and all the CO2 escaped. That means, again, it's going to shift forward. So the reaction's going, oh no, we lost the CO2. We have to make more, and it's going to shift to keep trying to make more and more CO2, to keep the balance point where it was. This is all happening because K is a constant, and if we did the math, everything has to shift to keep K the same. All right, so if we remove the bicarbonate, so if we take away the bicarbonate, this time it's going to shift reverse. So we're not going to say left and right. You don't even have to say forward and reverse. You can just do arrows. Isn't that wonderful? That's why Show Your Work's wonderful. And the arrows work. So if you take something away, you shift towards it. Here's our balance point. If we take a reactant away, we have to shift in the reverse to make more of the bicarbonate. Everything has to be there. All right, if you add more calcium carbonate, so if we increase the calcium carbonate, which is on the product side, the mistake most students make is they say it's going to shift reverse, but it doesn't shift. This one is no change. Why? It's like the trick question. Remember that question I asked, and Tiffany answered it correctly. You cross out solids and liquids. Remember we crossed it out? There's a reason we crossed
Because
it
this
out.
doesn't make a difference.
As long as it's there, it doesn't matter how much there is. It doesn't influence equilibrium as long as it's there. Now, if you took it away, it would make a difference. But adding more, no change because it's a solid. Solids and liquids, adding more has no impact at all. We're going to do one more thing with this, and that is I want you to write the K expression just for the heck of it. So I think the space up here was where I was going to write this. I don't know. Or else I was going to talk about yin and yang. So we have to all have a balance point. I don't know why I have a space up there. So K is products over reactants. We don't include solids and liquids. So lightly cross out your solids and liquids. So the only product I have is the CO2. No koi fish, so we just leave it. And then my reactant is calcium ion. So again, back to the question Katie had asked me about our final celebration. We're going to respect ion. So if it's an ion, we show the charge. And then our second ion is the bicarbonate. We'll squeeze it in next to Bill the cat. And that one I take to the second power because there is a koi fish. So Bill's showing entropy because of his hairdo. Stress tends to also increase our entropy until we realize that we can just stay in our own bliss. All right. So on the next one, a couple things that, again, can help. You can circle your equilibrium thing. This one, I have an extra piece of information that I gave you. And it goes back to that very first page. I gave you the delta H. What does this delta H tell us about this equation? Yeah, 50-50 chance. It's either exo or endo. So it's endo because delta H is positive. So this is endo, which means heat is a reactant. So this is something that helps most students is to add the heat into their equation. So you can just write it as heat. You can put the number, but the heat will be on the reactant side. Endothermic means heat is a reactant. So down here, this one's going to be exothermic, so we'll write the heat in on the product side. All right. Put your brackets. Put the heat in, and then put your brackets. So you have to stay within the brackets. I don't know why the brackets help students, but it does help a lot of students. All right, if we add the NOCl, so that's right here. If I add NOCl, I'm increasing this NOCl. It's going to have to shift forward. So again, when you add something, you're going to shift to use it up. So we're trying to use up the NOCl. You can't shift reverse because there's nowhere to go. You hit a wall, and the wall would make you go forward. All right, if we take away the NO, you don't have to show these up down arrows, but if the NO is gone, again, we're going to shift forward. So if you take something away, so we remove the NO, we have to move towards it. If you add something, you have to use it up. That's really the idea there. And that's really the principle behind natural medicine and Chinese, like Chinese medicine is what I'm familiar with. so in Chinese medicine, when somebody has an excess, like a fever, they help to reduce the fever, not suppress it, but they help the person to express it and let it out, is what herbs and such would do. All right, temperature means that we add heat. If we increase the temperature, we're adding heat. It's really simple. It's just like what we did. If we add heat, we have to use it. So it's going to shift forward. Right. So the heat has to go into the reaction because it's endo, it shifts forward. All right, pressure. For pressure, you look at moles of gas. Wow. Look at gas moles. So I have 2. And over here, I have 3. So pressure means, think of it like, well, you're pushing. Oh, wow, the moon just came up. I can see it from my window. It's just huge. Did anybody see the eclipse last night? So I tell you, I got up. I actually woke up at like 1:15, and I went outside, and there was the moon. It looked just like it does now. It was full, and it was luminous, and it was the silver color. And I came in because I was confused, because I'm like, there's supposed to be an eclipse, and I've seen enough eclipses. I know what they look like. And I Googled it, and it told me it was supposed to be a blood red eclipse, which really isn't blood red. It's still gray. And I went back outside because I had the time right, and the whole sky was covered with clouds. And so I'm figuring I was hallucinating in my sleep or something. But the pressure is going to push it together. So pressure pushes it together. So it shifts. High pressure moves to the side with fewer gas, moves to side with fewer gas moles. So it's pushing it together. It kind of makes sense. Over here you have NO and Cl2. This is the other comment I need to make, and it's probably because we're in this environment, and how some of you approach it is you'll look through your notes for the exact same example. However the equation is written, you need to do the equation for that problem how it is written. So you may see this equation again, like on a study set or worksheet, and it might be flipped. However it is written, this is my reactant, this is my product. If it's flipped, then how it's written, your reactant is always before the arrow, your product is always after the arrow. Yeah. All right, question E, you will see. So the idea is the equations are written for what they're trying to create. And so in this case, they're trying to create probably chlorine gas. Chlorine gas, for better or worse, is still used for chlorinating like water and stuff to kill the bacteria. In a lot of countries, they use ozone because you don't create all the chlorine byproducts and stuff. But what temperature? Well, we just said high temperature. So if we increase the temperature or a high temperature, that will shift it forward. Now, if we increase the pressure, it went the wrong way. So we don't want to increase the pressure. We want to decrease the pressure. So this was actually, oh, it's not on here, a gentleman known as Fritz Haber, who was German. If you've ever seen any movie in which they show the evil German scientist wearing the monocle, that is Fritz Haber. Fritz Haber was the father of chemical warfare. He had no morals. His wife was a famous chemist also, except that she was a woman 100 years ago, so she couldn't be famous. And so she committed suicide because she was so against what he was doing. But he won a Nobel Prize because he figured out how to do the Haber process, which is manipulating the temperature and pressure to make more ammonia which was then used as fertilizer to make more crops. So that was the beauty of what the gentleman did. He did later in his life have ethics came around, and so many people have to go through that dark side to find the light, I suppose. All right. The only one that changes the value of K is temperature. So all the other ones, going back, if we write our K expression, like actually on this one, we wrote our K expression. If you take away the CO2, it shifts to make more CO2. So this ratio stays the same. If we added more calcium, it shifts to use up the calcium. So the ratio stays the same. So any changes, if pressure changes actually the concentration because it changes the volume. And so the ratio stays the same. Temperature though, because heat is not part of the K expression, temperature will always change it. So this question asks, how will it change? So when we increase the temperature in this equation, it's shifted forward. That's going to increase your product. And our ratio is always product over reactant. So that's going to increase K value. On the first one, we can't do that because I didn't do the delta H, but we'll be able to do that on number 3. All right, so let's do number 3, and then we'll look at kinetics, and then we'll be done. So, all right, what's the first thing we're going to do? There's actually 2 things, 3 things. See the solid? Cross it out. Otherwise, and let's look at this. This is, yeah, add the heat. So this is saying delta H is less than 0. So it's saying it's a negative, which is XO, which means it's exiting. It's a product. So we'll pencil it in down here. So add the heat. On this case, if it's XO, it's on the product side. And then you don't have to put the brackets, but you don't have to cross out your solid liquid, but I want you all to get it right. And that's the idea. So the brackets do help a lot of students. So you can't go past the bracket. All right. So PCl3 is added. PCl3 is over here. If you add it, you have to use it. So if you add PCl3, you can't go forward. That's why we put the bracket there. Because you hit the wall. You don't want to hit the wall. You've all been there in life where you just keep hitting the wall, and it's really not worth it. This is Aikido. I don't know if you've ever heard that was the Japanese martial art. And so if somebody's attacking you, you just kind of step aside and let them fall. And so anyway, there's a wall. You're not going to hit the wall. If you add the PCl3, you're going to have to shift in the reverse direction. So you can just use arrows, or that means reverse. I will write the word also. Do not use left and right. It ends up being a disaster for most students. All right, chlorine is removed. So our chlorine's over here. If you take it away, it's not there. It has to be there. So we have to shift to make more of it. So again, we shift reverse. P4 is added. What's going to happen?
Shifts forward.
No change. Why?
I lied. It's because it's a solid. It doesn't.
That's why we're crossing it out, because if it's crossed out, it means there's no change. It's a solid. Solids and liquids, cross them out. You don't put them part of your K expression. All right, if we add heat, heat is on the product side. Again, it shifts reverse because it was exothermic. And pressure's increased. So we look at moles. So we have 6 moles, and on this side we have 4 moles. So if you increase the pressure, another way to think of pressure, and again, this is each person, if you increase the pressure, this is back to gas laws, pressure and volume are always related. It means you decrease the volume. You have less space, so you're going to have to shift forward to the side that has less. It's only look at the gas. Only the gas is affected by pressure and volume. Pressure and volume always have an opposite effect. For heat, you have to look at delta H. And again, for pressure, you look at the moles. All right, we're going to do two more things with this question. One is this question up here, condition, so we'll make it question F. What temperature and pressure will make it temperature and pressure? We'll shift it forward. And that would be, well, when we heat it, it went the wrong way. So we don't want to heat it. So we want a low temperature. And pressure, yeah, that worked. Pressure pushed it forward. So we want a high pressure. You can show arrows down and up. These are not always opposite. Unfortunately, my examples here, they were. They can both go in the same. They can both, it could be high, high, low, low. It's just however the equation works out. Temperature, again, is determined from the delta H, and pressure is determined from the moles. So they're figured out from two totally different things. The other thing I wanted to do is write the K expression. Just one last K expression before we do the kinetics. And so K equals, try purple. Looks the same. Product, so the PCl3 to the fourth power, and we ignore the solid, so the chlorine, and the chlorine is taken to the sixth power, and that's it. All right, one more page. This is question. All right, there's a whole page of these on the study set. Is kinetics. And that's what the lab is. The lab is the Chatelier's, and the video's there. And then there's another lab, which is the boron sulfur lab. And so it's like a half-hour video, and you listen, and then you just write your thoughts on like two of the things, or your thoughts about everything. So you just write a page about it. And there we go. It's kind of wraps up the whole term. I think they're both due Saturday. That's my hope. So kinetics, right, there was a pun intended. Kinetics is the rate of reaction. Oh, I know I'm getting done. Usually we're supposed to have our celebration 3 today, like way back when there wasn't the fires. Isn't that interesting? So everything got changed because of that. So we don't have a final. We have a celebration 3. So this is how fast. So how fast? There are 3 things that will make a reaction go faster. So we'll try it again. Tiffany's already got her point, so she's going to do the count. I just wrote a letter for somebody from my other class, and I actually put that in the letter, a recommendation for him, that he has to count to neon now before he's allowed to answer, try to give somebody else. Anybody, any idea what's going to make a reaction go faster?
Heat.
Heat. I have no idea who said that.
That was Kristen.
Okay. Thank you, Kristen. So
Surface area?
Yeah, I'm trying to think of a better way of saying surface area. So yeah, you could say surface area. I'm trying to think if it falls under my other category. I usually say just add more, increase the amount, or add more reactants. But surface area would would work for certain things. So if it was a gas, you'd have to add more reactants because changing the concentration. It's more with the solid that the surface area works. So if you smash up the solid, you're giving it more space, more area to react. The third one's actually the biggest one. I used it in the aspirin lab, phosphoric acid, and that is the catalyst. Just the catalyst. It was also what I used in my demo that finally worked. Or no, it did work. The one that made all the soapy suds, the Ki was the catalyst, the fairy dust. So we're going to go through why. So the why, always you're talking about collisions. Reactions are about collisions. And it was one of the first Nobel Prizes, was a famous equation that we're not going to work with, but it had to do with collisions and figuring out rates of reactions. So what happens with heat is when you add heat, you increase the jiggles and giggles, kinetic energy if you prefer. My son's has a different teacher for chemistry, and he did comment that he does miss the jiggles and giggles when the teacher, because they just did heat stuff, and he's like, yeah, he just says kinetic energy. But anyway, you increase the jiggles and giggles, and so many of you did the jiggle and giggle lab, and you do get more collisions. So if we were on the same classroom together and we started laughing and joking around and everything's more chaos, there's more chaos, you're going to increase the number of collisions. So with heat, stuff is jiggling and moving around more, and as things are moving around, so it's like giving kids a whole bunch of candy, and right, or after dessert on Thanksgiving, and the kids just start running around all over the place, and the adults are just like, I can't believe I ate the whole thing. So you're increasing the number of collisions, and you're increasing the impact of the collision. So think of it as a collision that happens on the interstate between two cars. A lot of damage is going to happen. A collision that happens between a shopping cart and your car in the parking lot, you usually don't even notice anything. But so if things are moving much faster, and that's what heat is doing, it's getting things jiggling and giggling. If you're adding more reactants, you're just increasing the probability of a collision. And so I don't remember who said the surface area, or that's the same idea. You're increasing the probability of the collision, of the reaction happening. The catalyst is the big one. So reactants, if you double the reactant, you double the rate. It's pretty much straight on. If you cut it in half, so there's half as much, you're going to cut the rate in half. Heat, for about every 10 degrees, it doubles. This is why we have refrigeration. So we slow down the spoiling of food by putting food away in the refrigerator. Catalyst, this is like a million-fold change. So that's why on the lab, it was the most missed thing on the post lab. It was question 2B. It said, what if she doesn't add the phosphoric acid? And most people go, it's just a catalyst, won't make a difference. I would still be there. It made the reaction a billion times faster. How fast the catalyst makes the reaction go is limited by the laws of physics of how fast things can collide. So a catalyst makes every collision perfect. Meaning a head-on. Every collision is perfect, or effective would be probably a more effective word to use. It aligns the reactants. Yeah. And so that's what a lot of people spend their whole time. In your car, the catalytic converter, platinum and palladium are really good acting as catalysts. All right. In our body, enzymes are our catalysts, they're biological catalysts, and they allow our body to happen in real time. Otherwise, all of our reactions would be much too slow. All right, so we're going to do a little bit of math. So here we go. Is this reaction exo or endothermic? And how do you know? You have a 50-50 chance. The kilocalories. It is exo. Yeah, 50-50 chance. That was a good guess. And it is because it is so, and that was actually, thank you for saying that, Philip, because if you see the symbol, which I did in number 2, I wrote this one like that on purpose because if you actually see the symbol of delta H, then you look at the sign. So this one is endo. And delta H's are always written after the equation. But I don't see the delta H, so this is saying this is a product. And as a product, it means it's exiting. So this is exothermic. So if I wrote the delta H, it would say delta H equals negative 890. All right, that's going to become important when we do part B. So how many grams of oxygen we're solving for is our grams of oxygen. And we start with 76.5 calories. And we're going to do a little railroad track. It's just part of the balance equation. Like everything we've done, it's just one more piece to go with the balance equation is there's always a change in heat. In our balance equation, it's in kilocalories because reactions give off a lot of heat. So 1,000 calories or 10 to the third calories to 1 kcal. So this is the same kilo as in kilogram and kilometer. That was actually the first lab. You guys had to do a bunch of metric. That was 9 weeks ago. Hard to believe. And then we bring in this number, the 890 kilocalories. And that number goes with the balanced equation. So since we're talking about oxygen, I will go to then 2 moles of oxygen. You can go from the kilocalories to anything in the equation. And again, sometimes I say kilojoules, because my other class, we always do it as joules. I don't know why in here we do it as kilocalories. All right, and then 1 mole of O2, you look at your handy dandy periodic table. I've always joked with my class, well, 2 things. One is that I should make the last exam just tell me everything you've learned about the periodic table, right? I joked that I would give them a blank periodic table and they just add all the pieces to it. It's like the names of the families, why they're in the same family, all that kind of stuff. And we would punch it in. Get a number. Here we go. It's going to be a really small number. They gave us calories, so sorry. 5.50 times 10 to the negative 3 grams of oxygen. Or if you want, what unit could I put on to get rid of the 10 to the negative 3? We could just go to milligrams because milli means 10 to the negative 3. So that was a swift, quick trick there. So energy coordinate, reaction coordinate diagrams. So we get to make our Cartesian coordinates along our X and Y axes. And this is going to be the reaction moving along. And this is going to be the heat change. And this is exothermic. So we're going to lose heat. So if you're going to lose heat, you're going to start high and end low. So it's going to be my reactants, my CH4 plus my 2 oxygens. And then down here is going to be my CO2 plus 2 H2Os. Notice I have not connected them because something happens to connect them. So But before we do that, we're going to show a line over here from where I start to where I end. This is my change delta H, and it was exo. So I lost heat. Endo, I would end up higher because I'm absorbing heat. All right, when you connect them, there is always a hump. There's always a hump. This won the Nobel Prize for the guy doing this. From where you start to the top of the hump, this is called E, capital E sub A, which stands for the activation energy. And it is always that. It's exactly what that is. It's the energy to activate it. So they have to have a certain amount of energy to them to react. So the enthalpy change was the delta H. And the activation energy we just talked about. There's our reactants and products. This is a negative delta H because we figured that out up there. So now we're going to show a catalyst. And this is why a catalyst is cool. A catalyst is the only thing that can lower an activation. So it can lower the EA. It gives it a new pathway. And that is why it is so fast. These energy diagrams are really crude, but basically the catalyst, I need another color, but we'll do, because the purple doesn't really show up. The catalyst cannot change the beginning and the end point. So the delta H is not affected, but it cuts out the activation energy. And then you can draw your little cat. He's looking very happy because he just lowered the activation. So it's like you don't have to climb over the hill anymore. You can just get right around it. And so that is why catalysts work so fast. The diagrams are not really that great for showing. All right, let's do number 2 and then we'll be done. So there's our equation. This is endothermic because I actually showed the symbol delta H. It's positive. Heat would be over on this side of the reaction if we wrote it in there. How much heat? So this time we're starting with 50 grams of hydrogen. It's a diatomic. And I want to know heat, which is kilocalories. So it just means you're doing your little factory label. Hydrogen is 1, so this is going to be like 2.02 grams to 1 mole. Label everything fully. That's the key. And then we need our balanced equation. There are 2 moles of hydrogen, and we just jump straight to the 50.6 kilocalories. And we punch it in our calculator. I have no idea what I just did with my calculator. Anyway, you got the idea. So that's the idea. You'll get an answer, and I believe that's interesting. The gnome must have taken it. I have a gnome here. All right, let's draw the energy diagram, and we'll be good. So this is our reaction moving forward. This is the heat. So the difference on this one, you're going to start low, and you're going to end high because it's endo. So our reactants are the nitrogen plus hydrogen. And our product is the N2H4. Sorry, 2 hydrogen. And so it's endo, its heat is going into it. When you connect them, there is always a hump. I don't care how big the hump is. There's always a hump. You can't go straight from here to there. That won a Nobel Prize, one of the very first Nobel Prizes. All right, we're going to label. So that's just saying that was the level I started at. You arbitrarily pick a level. The change from the beginning to the end. This is your delta H, and we put it, so this is like your bank account again. Here you just lost money in your bank account. Your bank account's ending up lower, and here you're putting money into it. Tiffany, did you just calculate that one?
Yeah,
What'd you get?
626 kcal. I think, if I did that right.
That's what I got too.
Good, thank you. So I don't know what my calculator. That's really weird. All right, the activation energy. Is from where? So the EA is from the start. Your reactance is your start to the top of the hill, top of the hump. So that's your activation energy. The delta H is from reactant to product. So it's just the difference between them. Hopefully that helps. So my activation energy is that from my reactant to the top of the hill. And then we get to draw the cat. The catalyst always removes the activation energy. So we get a new pathway. Do it with the red. So it just cuts it out so that you go from here straight to there. And then you can draw your cat meandering on there. Cat should have a tail. This is my stick cat. All right. So endo versus exo. 3 things that speed up a reaction: heat, more reactants, catalyst. That's it. All right, I'm going to stop unless there is a question. And